Hello, a very warm welcome from my side. My name is Bettina Duran, and we are having today the training workshop on biological waste treatment, part number 4, the detailed explanation of MYT and the MYT plant at ZAK. So here in the next slide, you just get for an orientation where we are. So it's the MYT technology and the MYT plant at ZAK. And as you see on the table below, what we're going to learn today is you have different wastes which you put in your treatment facility, and when you apply the MYT process, you get recyclables and the first part of the RDF through the mechanical treatment. And when you apply then the biological treatment, you receive the biogas, the other part of the RDF or the compost, depending how you set up your process. You become a leachate and you can separate the inerts, the inert material also from the waste stream. But we will have a very detailed look now into the MYT technology in the upcoming slides. So what we will deal with today is what does the name ZAK and the MYT business unit mean. We will also have a look into the history of waste disposal at the Kahlenberg site. We will see how the waste in Germany at the MYT plant looks like, what is the waste composition and the amount. And then we will also have an excursion to the collection systems and costs for waste disposal in Germany, just to give you an insight how we organize this here. Then we go into detail in the MYT process. So how is it set up? What are the important points? You will also learn about the output materials from the MYT process. Then how to use the RDF. And also what about the energy balance of the MYT process and the CO2 savings, because part of the waste is organic waste, and you can produce a CO2 neutral, climate neutral energy from this part of the waste. And we will see the other references with MYT technology here at the example of the Onut transfer station. Onut is in Bangkok. It's one of 3 transfer stations of this big city. And we will show you how MYT, how this process is set up to serve Bangkok. But let's start with the first topic. So what does the name ZAK and MYT business unit mean? So ZAK is a special purpose association which was formed in a legal communal cooperation between 2 counties, the Emmendingen County and the Ortenau Kreis. The ZAK is based in Ringsheim. This is just at the border of the 2 counties, and it serves more than 500,000 residents who generate about 100,000 tons of residual household waste per year. So they produce more than 100,000 tons of household waste, but the 100,000 tons is the residual waste and the organic waste. The ZAK's function is the waste management of the delivered waste via recycling, maximum yield extraction of biogas, RDF, and disposal. So its function is to really execute the waste management, to operate the MYT plant, and to make sure that the 2 counties are very well functioning concerning waste management. And then we have the MYT business unit. It is a company under private law, divested from ZAK, who is the sole owner. And the MYT business unit's function is to provide know-how transfer and advancement for MYT-based project. So actually, to put it short, ZAK is the operating company, the communal operating company of the waste treatment facility in Ringsheim for the 2 counties. And the MYT business unit is the company who supports the development and the execution of further international waste projects which apply the MYT process. So here we have the know-how, we have the patents, and we have all the knowledge and experience how to plan, to design, to build, and also to operate these facilities. So, where is ZAK located? Like I told you, you have OG for Ortenauer Kreis, and you have EM for Emmendingen. And where you see the red dot right at the border of the two counties, the MYT plant is located. This you can see on the right picture, and when you go to the left picture, you have the map of Germany, and you see that we are in Baden-Württemberg, which is in the south of Germany, close to the Swiss and to the French border. And when you look back to the picture where you have just Baden-Württemberg and the counties, you see that France is very close to our facility. And for example, we have here a wonderful example for a cross-border cooperation when it comes to waste management, because the city of Strasbourg, which is located in France, has the right to bring their household waste to the ZAK facility if they would encounter problems with the waste treatment facility in France itself. So we have a cross-border agreement, and it is a cross-border cooperation. So when it's needed, Strasbourg can make use of the MYT facility in Ringsheim. So let's have a look towards the history of waste disposal at the Kahlenberg site, because in Kahlenberg we have a very, very long history of waste disposal and waste treatment. So ZAK was already founded in 1971 until 73, and so that's 50 years from today back. And it was actually in conjunction with the commissioning of the landfill site, which was the first method actually to treat the waste also at ZAK. So this is how it actually always starts, or normally starts. It always starts with a landfill site. In 1997, there was then already the start of the district heating system and a pilot plant for MBT. At those days, of course, it was called MBT, Mechanical Biological Treatment, because the name MYT was not invented so far. And the district heating system came because the landfill was used substantially, the waste piled up, and there was sufficient landfill gas to harness. And this landfill gas was used in CHP systems and provided district heating for the community of Ringsheim. In 1998, the pre-planning of the MYT or the MBT plant at ZAK started, and from 2000 to 2003, the demonstration plant at ZAK was used, or was, the process was checked. And this is something I would like to tell you right now, right away. If you're looking for a process or for a treatment plant for Egypt, please check if the proposed system is already running in the world. You can only rely on processes or systems which are proven and which have shown already that they can run at least 8,000 hours per year. So this is 11 months of 12 months. You shouldn't have more downtime, and you shouldn't have more maintenance time for a waste treatment facility. This also applies to incineration facilities. 8,000 hours per year. You should be able to process your waste, and you should rely on your facility. So, and if you just encounter that the person is just selling an idea or something which was not really tested and running over several hours, please be patient, stay away, and wait until the person who's offering the system has put this in operation and can show you a real reference plant. Otherwise, it's extremely risky to try out a system which is not proven, especially in waste management. So in 2004, we had the honor to celebrate the cornerstone ceremony for the MYT facility at ZAK. So this is when the name maximum yield technology was invented. And that was right 1 year before in Germany we applied a very important law. From 2005 on, it is not allowed any longer in Germany to landfill untreated waste, untreated household waste. So any waste has to undergo a pre-treatment prior to landfilling. And this was just in line with the new MYT facility. So in 2006, we had the commissioning of the MYT plant at ZAK. And from this year on, the ZAK facility was processing more than 100,000 tons of waste every year, but we come to these numbers a bit later. And until now, but on 2014, the ZAK, who's always inventing and thinking how they can be more cost effective, how they can make use of the landfill site land, which is now available because the landfill is only in use in a very small site. The ZAK people were commissioning a biomass power plant. And this biomass power plant is just supporting the district heating network from the landfill gas. And this biomass heating plant makes use of a special grass, which they grow at ZAK landfill site. It's a grass which contains a lot of energy. It's grown over the summertime, then dried and stored. And during winter, when the town of Ringsheim needs more district heating, then the power plant is put in use and the hay is fired for producing heating energy. In 2016, as you see, we were able to celebrate 10 years anniversary of the MYT treatment facility. And this is when the facility already processed more than 1 million tons of untreated residual MSW. And from 2020 onwards, ZAK received the permit for making use of the produced RDF on site. So ZAK is now allowed to install their own power plant and to make use of the RDF for heating and electricity generation. And what is very special about this facility also is the phosphor, which is within the waste, will be recycled, will be recovered actually out of this incineration process from the ashes. So I show you now some pictures of how the waste treatment facility or how ZAK looked in former times when it was an old iron mine. So you see the open phase mining. So there were approximately 10 million tons of material extracted. And then you see also the deep mining, so approximately 5 million tons of material extracted over the time. And this is an old iron mine, and this old iron mine at Kahlenberg was used then as the old was then used as a landfill. So this, what you see here in the pictures, was how it looked like before they made use of it as a landfill. And on the next slide, you see how ZAK looks today. On the bottom, you see 5 buildings. These are the buildings of the MYT process. And on the back of the picture, you can still see the old landfill. Most of it is already renaturated and covered, also with grass. And then you see also a place where the landfill is still covered with foil, plastic foil. And this is where the landfill is also still in operation. Now I show you a picture how it looked like from 73, from the commissioning of the landfill site, until 2005, when MYT was put into operation. It's just a landfill site, and we have about 6 million tons of waste sitting there. And this is how everything started. And why we show you also the history is to encourage you that it always starts with a landfill site. And from there, you go make your steps until hopefully soon you end in circular economy, where dump sites are not needed anymore. Maybe only for ashes and inert material, but this is not a problem because it's not harming anymore the environment. So you've seen the plastic foils in the picture where you've seen the landfill site on the backs. Here you have a close-up. the coverage of the landfill site is to reduce the odor and dust nuisance, which you normally have from landfill sites. And this is here especially important because you see on the back of the picture, you see the vineyards, because the ZAK plant is actually located in a black forest in southern Germany, as you've seen on the picture before. But this is also an agricultural area where a lot of wine is and other crops are growing. So of course, the ZAK had to take a lot of care with the waste to not contaminate the fields around. And here you see the landfill is covered. They spray water to avoid the dust, and the coverage of the landfill avoids most of the odor or reduces it tremendously. And the coverage is just a foil, and you put all tires on top of it to avoid that the wind is blowing the foils away. And now you can see how most of the old landfill site look like today. So it's after renaturalization, it became a habitat for many rare animals and plants. And this I just want to share with you. You've seen the picture from the iron mine, you have seen the pictures from the landfill, but after renaturalization, we have now very rare animals coming back and also orchideas. Now there are 16 different types of orchideas growing on the old landfill site, which is just beautiful that nature has the ability to come back after what we've done to it. And furthermore, the landfill site is now a popular conservation area and a destination for families. So around the landfill sites, you have sort of nearly a petting zoo. You have donkeys, goats, sheep, pigs. People can come. You have picnic areas. It's open to the public, which is not normal for a waste treatment facility. So people can just come and see and sit and enjoy themselves. And they also do not have to suffer the bad smells, because the ZAK process or the MYT process takes care of it. We come to this later. I will show you how we can avoid the odor nuisance around the MYT facility. So why is ZAK doing all this? So what drives the ZAK to build the MYT facility? Of course, the most important reason always are the laws, laws and regulations in a country. So this is very important, that Egypt is establishing a good framework so that the processes and the waste management can follow. So ZAK had to comply with the European Waste Framework Directive. And of course, the German waste legislation, which is the EU Waste Framework Directive brought into German circular economy law, the Kreislaufwirtschaftsgesetz. Because if Europe decides something, all the members of the European Union have to translate the European law into their national law. This is what the second point means. Of course, ZAK also wanted to protect the natural resources and wanted to make the best possible protection of humans and the environment. Also when it comes to emissions, odor, dust, noise. They were also driven by the technology. You need to know that MYT is also best available technology. It was awarded by the Umweltbundesamt, by the Environmental Federal Agency of Germany. And of course, the economic efficiency, a proper relation between costs incurred and the technology chosen. And this is also a very, very important point for you to know for your decisions in what technology to invest. Please have a look on the treatment costs per ton of waste. So the waste composition and the waste amount as our third topic. So let's have a look how the waste in Germany looks like, which goes into the MYT process. So you have about, here in this table, just to make it clear to you, you have, of course, the wet, the fresh waste proportion. This is how it is delivered to the plant with the moisture or the, the moisture content or the humidity which is still in, pardon, and the dry matter content of this material. So we have about 30% kitchen or garden waste, so biogenic waste, which goes into the MYT treatment facility, which has only a dry matter of 30%. We have paper cardboard, only 3%, which is very normal in Germany because paper and cardboard are collected separately. People have a separate paper bin in front of their door, so only minor amounts of paper and cardboard should be found in the residual waste. And this has a dry matter approximately of 70%. You also find textiles, but these are more rags because also textiles are collected separately in Germany. We have big boxes where you can bring your old clothes, your shoes, which are still usable, but you don't need them anymore. You can bring them to special containers in the streets in Germany. Then we have about 10% plastics still, because actually plastics are collected separately in Germany in the yellow bag, but we come to this later on. But still we have about 10% of plastics, and wood and other combustibles 14%, glass inerts 11%, which is quite high because also glass is collected separately in Germany in containers on the streets. We have a small amount of metals, which also shouldn't be in this waste at all because they are normally collected separately, also in the yellow bag. But as you see here also on our waste characteristics, there are always people who throw incorrectly, who are not separating at source how it should be. And this is the beauty, the beauty of the MYT system. So the people can sort and separate at source, but what the people did wrong and put in the residual waste, MYT is recovering it. So if you have incorrect throws, if you have recyclables still inside the residual waste, it is recovered by the MYT process and diverted from the landfills. And of course we have a fine fraction and other wastes. So this is what goes into the facility, and when you look towards the pie chart on the other side, this is our output. This material gives us nearly 40% of water, which is completely recovered and diverted from this waste. So this water is in Germany, we cannot make really use of it. We have our own wastewater treatment plant because the communal wastewater treatment plant was not designed to take water from a waste treatment facility. So ZAK has its own water treatment. And then that's it. So the water is just treated and not used further. But it's actually a pity because this 30% water could be used easily for agricultural irrigation purposes, or you can process it also for industrial water use. So actually just to clean it and not to make use of the water is a pity, but we do not have another option here in Germany. When it comes to the design of such a waste treatment facility in Egypt, of course we will think about what to do with the water, how to use it in the vicinity of the area. Actually, technology would also allow to make drinking water out of this water, but from a psychological perspective, actually people would not like or do not like to drink water which was inside wastes. So of course, we are not doing it, but technically this is all possible. Just to make you think that you make please use out of the water which is in the waste and which we divert with this process. Of course, we regain all the minerals which are in the waste, or more or less all the minerals and all the metals. And the biogenic waste fraction is converted into biogas. Here in Germany, we have only 30% of bio-waste, but when it comes to Egypt, where we have a higher share of bio-waste, of course, the biogas yield will be higher than 5%. And we regain the other waste material as refuse-derived fuels, as RDF, which can be used in industrial processes for generating heating energy, cooling energy, electricity, process steam, you name it, just for industrial applications and what is necessary. And of course, you can also optimize power plants for a higher electricity output, or you could also co-incinerate these fuels from the MYT process in industrial power plants, like it is done in Germany also. And you can also co-incinerate this fuel with hard coal or other coal. So you have all the options. So here you see the statistics, how much waste was processed by the MYT facility. So it started in 2006, of course, half in the year, so the amount is not 100,000 tons, but more than 50,000 tons. And you see that over 10, 11 years, the amount of waste produced by the citizens was nearly the same. And just to show you here, the dark column shows the total amount of waste which was processed in the facility. The lighter brown column is the waste generated by the two counties, Ortenau and Emmendingen Kreis, and the very small gray column at the side is waste which came from other areas, which are not in the normal contract. So maybe they came from France or from Switzerland or from a different county, from a different area, and who had just problems with their waste treatment facility. And the ZAK or the MYT process is flexible enough to take on different wastes also, if needed. So, and now we make an excursion to the collection systems and costs for waste disposal in Germany. This has nothing to do with the MYT process. It's something different. And later on, after this section, we go into the detailed explanation of the MYT process. So, here I want to show you the waste composition in Germany. So, household waste is just 30% of the waste which is arising in Germany. So in this 30%, this light green, you have household waste, commercial waste, which was collected jointly via the public waste collection system. Then you have a bulky waste. You have the waste from the organic waste bin, which is normally collected separately in Germany. But when you are connected to an MYT system, you will not have to fill another bin with organic waste. You can just use the residual waste bin and put the organic waste on top, because MYT is dependent on the organic waste for the process. Then there is a 12% share of garden and park waste, which is biodegradable, which goes also into bio-waste treatment facilities. Then we have about 5.6% glass, paper and cardboard, a mixed packaging, recyclables material. Those are all collected separately. They are not in the residual waste. The old electric equipment is collected, and others like composites, metals, textiles. So this is how the waste in Germany looks for households typically. And what we introduced in 1994 in Germany is a quantity-dependent waste fee system. So you pay your waste fee according to the size of your bin. Means your household is producing a lot of waste, you pay a higher fee. You reduce the waste at your household, you need only a smaller bin, you pay a lower fee. So that means that the homeowners choose the size needed themselves, so they can choose. And but what you need to know is it's not a linear system. So when you're doubling the bin size, you do not have the double costs, because actually also if you only go for the smallest bin, 35 liters, and wanted it emptied only once a month, of course you have to pay a basis fee, because the trucks have to come, they have to empty it, and the treatment facilities have to run. So the basic price is the basic price, but when you double the bin, you don't have to pay double, you just pay a plus. And if you have just in 1 month or in a certain period, you have to dispose of more waste, you can also buy bags, and by buying the bags, the costs for the extra waste are covered. So with this slide, we want to show you again how Germany is set up. So the glass is collected separately, the paper is collected separately, the packaging is collected separately, but from the packaging you find quite a big portion also in the waste which goes to the MYT facility. And then we have the brown and the gray bin. The brown bin is for bio waste and the gray bin is for the residual waste. And at the ZAK facility, the people have only one bin for organic and residual waste. This goes all in one bin, and it's much easier for them because nobody really enjoys towing out the bins in the morning, and if you have less bins, you have less efforts to do. So, and now we make the excursion towards the yellow bag. This is the packaging waste. So here, the yellow bag is financed by the private sector. This is important. So that's the people, the citizens do not have to pay for this yellow bag. It's financed by the private sector, and it's a part of the so-called dual system in Germany. And this system complements the public waste disposal system. And within this system, the industry and trade, they pay a license fee for the use of the packaging. And we have 10 companies in Germany which have this license, and the industry can just pick or choose one of the 10. To them, they pay the fees. The companies, these 10 companies use the income for the licenses to finance the disposal and the recycling of the packaging. So these companies have to invest into treatment facilities which are able to recover and recycle the material of the yellow bag. And the normal household waste, on the other hand, is taken care of by the city and the municipalities. So the household waste is the household waste, and the packaging waste is taken care of by the private sector. So just give us the opportunity to also to show you the new packaging law, which we have since January 2019 in Germany. And we just want to show you the most important cornerstones for the manufacturers and the retailers. So from 2019 onwards, the participation in the system is an obligation. So you cannot choose to be part or not be part. You're obligated to be part. And you have to register your company. You also have to report all the data. And what is also new is you have to declare that all the data is complete, because in former times maybe you just reported some data but not all the data. And if you do not comply with these new packaging laws, there are also fines which you have to pay. So it's much stricter than it was before. And here are the recycling quotas for the individual packaging materials which we want to achieve now. They have changed, and I just wanted to give you the numbers. So 85% now for paper, cardboard, carton, and so on, and from 22, 90%. 80% for glass, ferrous materials, and aluminium. 75% for beverage cartons. 55% for composite packaging, and 50% plastic, metal, and composite packaging that has been emptied of its residues. Yes, and these are the numbers we have to achieve now here. So we would also like to give you an insight on the waste fee ranking, and we just took the year 2019 for an example. And it shows you the waste tariffs of the 100 largest cities in Germany, largest cities in terms of population. And what we do in Germany to make really comparisons, because it's different from municipality to municipality, from county to county, there are big differences in Germany, but somehow we need to compare the tariffs and the models. So we come up with a model household in Germany, and a model household consists of 2 adults and 2 children. And it includes 4 types of waste which this model household produces. It's the residual waste, the organic waste, the bulky waste, and the waste paper. And like I said, there are so many differences from county to county, so also the collection rhythms and the service levels differ between the cities. So it's not so easy to make a real comparison, but this is these are the findings which we came up with in Germany. So in the tariff models of many cities, the amount of residual waste is a decisive factor for the calculation. So you don't look towards the bio waste or the paper, you look towards the residual waste. And the comparison assumes an average volume of 60 liters of residual waste per household and week. So we estimate in Germany that one person generates about 15 liters of waste per week. So the model household needs a 60-liter bin per week. But many cities specify the quantity as the minimum storage volume. So 60 liters is, this depends, it really depends. 60 liters is fine for some families, but others need more space. So the volume of the organic waste is assumed to be 20 liters per household per week. And of course, there are still some cities in Germany which still do not have an organic waste bin, because you can also make an exemption with this. For example, if you're in a very rural area and the long distances and the small amount of people living in the area does not justify an additional logistic route, additional bins, and the costs occurred would be too high, areas can still skip this organic waste bin in Germany, but actually by law you need to have it, but you can go for an exception in writing and receive this exception also. Okay, and the bulky waste collection is seen at 2 cubic meters per year, so per model household. A paper bin must be available, but there is no explicit quantity which has to be collected. But the statistical data tells us 72 kilograms per person and per year are collected on average in Germany. Of course, for conversion purposes, we estimate a mass density of 0.1 kilogram per liter for residual waste and 0.15 kilogram per liter for organic waste and 0.17 kilograms per liter per waste paper. That's just for conversion purposes. And a weekly collection would be 52 emptyings per year, and for a fortnightly collection, 26 emptyings per year. But there are also areas where you can choose emptying once a month only, which is then the lowest fee. And if you combine this with a small bin, then you have the lowest waste fees in Germany. So, and what about the waste fees in Kahlenberg? Just to compare the fees. You can see here so these are the waste fees. And actually always for the same service for the citizens. But why so big differences in the costs? This depends on the waste treatment facility you're connected to. If you see Ortenauer Emmendinger Kreis, down the people who are collected to the waste treatment facility at ZAK, at Ringsheim, they have the lowest waste fees in all Germany. If you go to the top of the list, you only see incineration facilities. Mannheim has an incineration facility. Freiburg has an incineration facility. And to operate incinerators is so much costly than operating MYT facilities. So, and the people who just live there, they cannot choose. They have to pay the fees set up by the county or by the municipality according to the waste treatment facilities and the costs which occur there, because it's a communal system. There is no exception. But the wonderful message actually here is you can have a system so sophisticated like MYT, which is the best available technology, and still the fees are very low. Okay, and now let's tackle this mysterious MYT process, and let's have a really deep insight how this process functions. Here, with this slide, we just want to show you how the waste treatment trends in Europe developed over time. So at the beginning, it was only landfilling. Then we set up many incineration facilities in Germany. And then the MBT facilities came. And when we have a look, and now, of course, you have a lot of sorting, you have MBT, and you try to make use as much as possible out of the waste, which also shows you the hierarchy on the right side. But here it is only the food and drink material. So here it's only the material, organic material. So the best thing is always if you can prevent producing waste. But if you cannot prevent it, maybe you can redistribute some foods and drink to people who need it when it's still good. And the third way to preserve actually this resource would be to send it as animal feed, or to make animal foodstuff out of this organic waste. If the prevention of making it a waste is not possible and you end up with a waste, you have three options. The most preferred one is the recycling option. So if it's food waste, of course, you would send it to an anaerobic digestion or to a composting facility, depending on how this material looks like. If this is not possible, then of course you try to recover it and try to recover at least the energy which is in the waste. But if it's really wet material or drinks, that doesn't make really sense. By incinerating it, you would need additional fire to make this material, to transform it into ashes. And the last preferred solution is the disposal. So only the incineration without recovery. You send it to landfill, or it goes into a sewer, of course, if it's a drinking material and you flush it down the toilets, whatever. Okay, but now MYT. You see the waste which is delivered to our facility on the small picture. And by applying the MYT process, we produce from this waste refuse-derived fuels and biogas, so two types of energy carriers. We recover the water and the recyclables which are still in this waste, and also the metals, also the minerals. And then we have a small rest of residual waste, which we cannot put in any category, or which we do not want to put in any category here, because, for example, there are some materials which we better landfill than transforming it to RDF, because burning or firing this material would cause very harmful emissions, which are difficult and expensive to clean in the flue gas cleaning system. So sometimes it's better to decide to put a certain piece or a material on a landfill site instead of incinerating it. And this is why you also need to know your waste and where it comes from. That makes this decision much easier. And of course, we have also a small portion of losses. This is actually more or less the bio waste. where we have the losses, because we are using the microorganisms, and these billions of microorganisms which are inside this MYT plant in the process, they have to feed on organic material to produce methane or to produce heating energy, and this is why we also have losses in this process. Okay, so here, just to go back to the history, we start with the demonstration plant at ZAK, where the MYT process was first tried out if it is really not a fancy idea, but a process which is reliable and which can process waste. So this is what we are looking at now. Here you see the demonstration plant which was erected at ZAK. The trials went over 4 years regarding sieving, classification, and digestion, and then the ZAK process was the patent was developed, and then they had 3 years on a technical scale, so 15,000 tons per year, a small demonstration plant to see if the mixing and the process water, if this also all works together. And if you see this development time, 4 years preparation and 3 years of demonstration facility. And then the reference facility was built. So this shows you also that in waste management and waste treatment, you need patience and you need time. So because also the design, the planning, the project development needs at least 2 years, 2 to 5 years. Then you set up this facility, then you do the commissioning, then you process the waste, and then more or less you know if you have taken the right decision, the right facility for your waste, or if you wasted all the investment, if this process is not working or if your plant is not functioning well. So this shows you that you need a lot of time within waste management to find out if something is really working or not working, and you need patience, like I already said. Here, our process steps. Like I told you, it's a 5-step system, and I will show you also. So we have 1 step in the building, which I show you on the next slide. The first step, of course, is the waste acceptance, where we inspect the waste. So we look what is inside, and we also dose the waste into the system. And in the waste acceptance, we already exclude the minerals, the metals, and residual materials from the waste stream. In step number 2, which is the mechanical pre-treatment, we do the sieving, the classification, and again an inspection. And here, in this step, we exclude all the recyclables, which are still in the waste, from the waste stream. Also the minerals, which are big enough. Of course, the metals, which can be taken out by magnets and also by hand. Fuels, but these are special fuels here. This is mainly plastic, so big plastic foils. So the fuels which can be excluded here, and of course residual materials which we want to exclude because they could harm our bacteria or harm the process or the system or any components. Then the third step. The third step is the heart of the process, which is the biological step. Here we have an interim storage and also the defined anaerobic mixing process, so the DAMP. And I show you in the pictures later how it really works. But what is also part of step number 3 is the water treatment, where we clean and regain the water and produce the biogas. And we have also the discharged air treatment. So we clean the air which we do not use anymore, which is in the halls and which we use. I show you the air flow management concept later on also. And here we work with 2 different systems. We have 3 actually. We have scrubbers, so we have washing, we have biofilters, and we have also a regenerative thermal oxidation. The RTO is only used in Germany. This is something which we have to apply by law. It's a special thing. If you have questions, you can come to me and we can discuss it. But an RTO, for example, would not be needed to operate such a system in Egypt. The 4th step is the biological drying step, where we dry the waste material and homogenize it. And in step number 5, we have mechanical material separation. It's again sieving, classification, and also loading of trucks to dispatch our RDF trucks. But here we separated very small minerals and metals, which you cannot get hold on in step number 2, because first the material has to be dry and also homogeneous to take the metals and minerals out. And of course, the biggest portion of fuels is produced in step number 5. So let's have a look on the different steps. So here, this is step number 1. So waste acceptance. The next one is step number 2, which is the mechanical pre-processing or the mechanical pre-treatment. Then we have step number 3, the heart of the facilities, the biological treatment, and also on top of this red box you see the biogas fermenters already. Then we have step number 4, which is the biological drying process, and step number 5, mechanical post-treatment. Now you can see our waste acceptance hall. The first thing which you should notice is that it is a flat bunker. It's not a deep bunker. Of course, we could also set up a deep bunker, and there are MYT facilities which operate with a deep bunker. But here in Kahlenberg, it is extremely important to us to know what is inside the waste. So when the trucks come in and unload, they put this waste on the flat bunker, and then it can be inspected. And if they are, for example, motor blocks or big trunks inside, which we already had, we can exclude these big parts here and treat them separately, because if we would just put them in the system, they would block our process, they would harm our components, the sieve drum for example, and then we would have increased maintenance and also costs. So we work with a flat bunker here to see what is inside the waste. On the left side at the end of the flat bunker, you see a pile of scrap metal. These are old metals. It's just an interim storage here, and it's quite a big pile. And actually, these metals should have never come to these facilities, because normally they are collected separately in Germany within the yellow bag. But as I told you already, people also in Germany do incorrect throws. They separate not always correctly. And this is how we can regain all these metals with the MYT process. Here you see how the machinery is pushing the waste towards the first entry to the conveyor belt, and so the crane is dosing the waste onto the conveyor belts, and from the waste acceptance onwards we have 2 parallel lines, so we have 2 conveyor belts starting in this acceptance hall, which is extremely important. This gives us a lot of flexibility, and we can also operate this facility by doing maintenance on one line. So we can always process waste in this facilities on 365 days a year. This gives us flexibility, it's cost effective, and it's wonderful also for our contractors, because they know when they bring the waste here, we can always process it. They don't have to go to another facility. Now you have an insight into step number 2, the mechanical pre-treatment. In this setup, in this technical setup for Kahlenberg, it looks like the following. You have a big sieve drum with bag openers. I'll show you in the picture on the next slide. You have also ballistic separators for separating the heavy and the light fraction, and we have 2 manual sorting cabins here in this setup. So one sorting cabin is checking the sieve overflow, so the big parts of the waste, and the other sorting cabin is checking the middle fraction of the heavy fraction from the ballistic separator. This is where the valuable material is in, and where we separate also material which we do not want to have in this process. This could look differently in Egypt. It depends very much on the waste characteristics, how to set up the mechanical pretreatment. And the picture here is taken when this plant was more than 10 years of age. And it looks very clean and very new, but this is also part of the MYT concept, that everything is maintained clean, because if the facility is clean, you can see if you have oils dropping down, if something is wrong with the machinery, and you can repair it right away. When the facility is very dirty, you will have a bigger maintenance effort altogether than when keeping it clean. Here you can see the drum sieve with the back openers, with these claws, how big this is. With this drum sieve, we create 3 different fractions. So like I told you, so it's the first one is the small fraction, where most of the organic is in. This fraction is not sorted, not by hand, only magnets take away the metals which are still in. And the big part with the fine fraction with the organic goes directly to step number 3. Then we have a middle fraction here, which goes towards the ballistic separator. And we have a sieve overflow. These are the big parts of the waste. So this sieve drum is creating 3 different fractions. Here you see on the next slide, you see the heavy minerals which we exclude from the waste stream. And they come through the ballistic separator, so it's middle size fraction. They get sorted by hand. Then they are excluded by hand. And it's incredible what people are putting in the waste bin. So also stones, quite a lot amount of stones, and a big amount of metal scrap, which, I repeat myself, should not be in our waste. We only get the residual waste, and still so many metals are in. So, and these metals, of course, are sold then to scrap dealers, and this is done with the recyclables also. Now I show you step number 3, how this step number 3 is working. It's a multi-zone reactor in the defined aerobic mixing process. So what you have here is a horizontal half bowl of concrete with a horizontal agitator, the mixer. So the waste is going into this mixer on a continuous basis, and process water is applied onto the waste. This is why the MYT process is not impressed about the water content of the waste which is coming to the facility, because we are adding process water to the waste. Just to give you an idea, for 1 ton of residual waste, we apply 1 to 1.5 tons of process water. So we really are creating a slurry in this mixer. The waste and the process water stay in the mixer approximately 2 to 3 days, and they get mixed very, very slowly. So 1 turn is about 2 minutes. So it turns very, very slowly around. After 2 to 3 days of mixing, the waste from the entry of the mixer was passed through until the end of the mixer, and then is pressed. Here with the press, we separate the solid material from the liquid material. Within the liquid material, we have now all the dissolved organics, where we make biogas out of it. And it is extremely important to make this clear here with this slide. We create from the waste 2 phases. We create a liquid phase, which goes to the biogas production, and we create the solid material, which is the press material, which goes into the biological drying process. I show you a picture of how it looks inside the mixer. The next slide. What you also can see here is that there is not a biogas production in this step. This is a hydrolysis. Here it's the preparation for biogas production. The waste is mixed with the process water and turned around. The aim is the aim here is also to reduce the pollutant content of the waste. By applying the process water, the salts are also washed out of the waste or reduced. So this is why we can create a very high quality in RDF, because the pollutant content is reduced and can also be controlled by washing. And as I told you, here we are working here with oxygen, so we are aerobic. It's an aerobic mixing process. It's the hydrolysis, so the first step of the biogas production, the preparation for the biogas production, because the organic material is dissolved into the process water. This is what is happening here. It's very important. Yes, I think this is what to tell you here. On the next slide, you see how this slurry looks like after 2 to 3 days of mixing. It's reduced in size, so we do not need a shredder to reduce the size. A shredder actually requires a lot of electricity and it's expensive in the operation. With this mixing, you reduce it automatically because the material is just pushed towards each other. It's also washed, and the waste is much more homogenized as before, so the slurry looks quite even all over. Here you have a picture of step number 3, of hole number 3. So you see 6 mixers, and every mixer has its own screw press underneath. So when I told you in the beginning we have 2 entry points, 2 conveyor belts, 2 parallel lines. When it comes, so this is true for step number 1, the waste acceptance, and step number 2, the mechanical pre-treatment. But when it comes to step number 3, we have 6 parallel lines already. So of course it's easy to conduct maintenance and cleaning on one mixer, on one screw press, and 5 other mixers and presses are still in operation and can process the waste. So the press water, like I told you, is going to the biogas fermenters. And we have here 3 biogas fermenters, 2,000 cubic meters of volume. The process water stays in one fermenter approximately only 10 days. So that shows you how fast this process is. Because if you put solid material, if you put bio-waste into fermenters, you need 23, 30, 40 or even more days for the biogas conversion. And that means for you that you need, if the process is slow and if this material has to stay for a very long time in the fermenters, you need more volume and more fermenters. And also if you put solid material into fermenters, you have much more cleaning efforts as if you only put process water into the fermenters. So it's much more easy to handle. And in addition, you have a great yield in methane. So our biogas has a 75% methane already. And just with a bit of gas cleaning, we can use it directly in our CHP systems, which we had from the landfill gas usage. And in our days today, there is not much landfill gas coming out of the landfill anymore. I mean, it was more or less closed in 2005, but still there is some yield, not sufficient to make it use in the CHP systems alone, but if we blend it with our freshly produced biogas, we can still make use of the old landfill gas, so, which is quite a good application. Here you have the insight now into one of the drying tunnels. So the waste is put into the drying tunnels from the ceiling. You see the hole in the ceiling, and and then it is put here into the drying tunnels. And what you need for achieving a really great RDF after the drying process is the following. You need a loose and homogeneous and air-flowing friendly material which you can put into the tunnels, because biological drying means that you put the waste into the tunnel and then you blow air from underneath through the waste until the ceiling. So you provide a lot of air into the waste, and this is how the microorganisms which are inside the waste receive the oxygen. And with the oxygen, they produce heating energy. They feed on the organic compounds, they produce heating energy, and this is the energy we use for the drying process. So it's completely biological. But after the mixing, after the presses, the waste has a constant moisture content of approximately 55 to 60%. So this is ideal because it's all homogeneous. And it's an aerobic pre-treated material. This is also extremely important. If you put the waste material into anaerobic digestion, into the fermenters, you are in an anaerobic milieu and you will have different bacteria, different microorganisms. To make the change from anaerobic to aerobic is extremely difficult and takes a lot of time because the microorganisms have to change inside the waste. So if you have an aerobic pre-treated material, it's extremely easy to apply biological drying. If you have waste material coming out of fermenters, it is nearly impossible to gain good drying results because you have the wrong microorganisms inside. These are microorganisms which produce methane and not microorganisms which can produce heating energy. You need the ones for heating energy for the drying process. So please take care of this. Don't try to dry biologically waste material coming out of fermenters. It's extremely difficult and you won't get good results. Just for showing you the size of one tunnel, it's quite big. The waste is put in, as I told you, from the ceiling. And then it stays in one tunnel for only 4 days. Air is blown from the bottom to the top through the waste material that the microorganisms are supplied with sufficient oxygen. And after 4 days of intensive drying, the waste is taken out and put in another tunnel for additional 4 days. Why do we not leave this material inside just in one tunnel for 8 days? You will always have dead zones where you do not get the oxygen towards. So by taking the material out and putting it into the tunnel again, we avoid the dead zones because everything is mixed and homogenized again. So this is how we can make sure that all waste in one tunnel is dried down to less than 10% moisture content. The discharge of the tunnels is done by an aggregate, by this machine which you see here. So the moving floor is pushing the waste towards this machinery, and this machinery takes the waste out of the tunnel. And this indicates also to you that this step is completely automated. I'll show you in the next picture. This is this aggregate in front of a drying tunnel taking out the waste material. It doesn't matter how many drying tunnels you have, you need only 2 to 3 people here because everything is automated. On the next slide, you see the RDF material before drying, so after the presses. This is on the left side when it's wet, and on the right side you see the waste material after drying when it has only 10% moisture left. And now I go with you to the airflow concept of the MYT facility at Kahlenberg. You see on the top that the fresh air is first entering the machine halls in the facility buildings. And all machinery is completely enclosed so that the point sources can be suctioned off. The air from the facility buildings is collected as exhaust air. And this exhaust air is used for ventilation for the mixers, is used as supply air for the drying tunnels, and of course we have some excess air which we do not need for the mixers and which we do not need for the drying tunnels. This air is just moistened and then cleaned in the biofilters. So biofilters are just containers filled with an organic material like bark mulch, and it's also with the usage of microorganisms. They help us to filter the air and to clean it and to take away the odor particles out of the air. The air which is used for the MZRs, for the multi-zone reactors, has to undergo an alkaline air scrubbing, and then also together with the air from the drying tunnels, an acid air scrubbing, and then we burn this air in the regenerative thermal oxidizer with our biogas. The RTO, the regenerative thermal oxidizer, is only used in Germany by law. I told you before we would not have to use it for Egypt, and this is good because it's costly in operation, and we also need to use our biogas, which we would actually prefer to use for electricity production. But these are just our framework conditions in Germany which we have to apply to. That's just fine. What I just also want to tell you is that all machines are tightly encapsulated and controlled and monitored. So the air extraction is monitored. We have also an airtight building construction. And actually, we go so far that we have negative pressure into our buildings, that the air which is polluted with odor cannot leave the buildings. Only fresh air can get into the buildings, but polluted air and emissions cannot get out of the buildings. This is why we have them with negative pressure in Germany. We make multiple use of the extracted air volume. Like I told you, first we use it in the facility buildings, and then we use it for ventilation and as supply air. We have a differentiated flexible air treatment process, so we clean the air accordingly to their pollution, and we do not clean all the air with one system. We distinguish which air we clean with what. And so we have a consequential cleanliness and maintenance of all the equipment, and we minimize the emission exposure to the personnel. So this is where we can keep our staff as healthy and happy as also staff in the office, because we have, I show you on the next slide, if you do the emission measurement for securing the protection of the working place, we can demonstrate how good we are with our measurements, with our pollution actual level. I show you on the next slide how far ZAK is driving this. We have here, or actually just to start with this, so the workplaces have to be set up such that the emission limits can be measured and upheld on a permanent basis. And to ensure the emission protection, the measurements of hazardous substances must be carried out on a periodic basis. And when you see the measured values and the limiting values, which we have here in Germany on dust, it's mainly dust, but it's also with the front-end loader, the step 1 to 2, and the step number 4, there we also measure the substances. And when you see the dust levels in step number 5, which are measured with 0.43 and the limiting values with 10, and also when it comes to mold and mildew power, front-end loader step 1, you see how far away we can, how far away we stay from the limiting values when it comes to dust. So with the MYT, if you want to, the humans and the environment can be protected very efficiently. Here you have insight to step number 5, which is our last step. The goal here is to create a specified homogeneous RDF. Here in Ringsheim, we are producing 6 different fractions of fuel. They differ from particle size and calorific value because we have different users or buyers of these fuels. One part is going to the cement industry, another part is going to a paper mill, to the industrial power plant. Other portion is going to a communal power plant where hard coal is fired for producing a district heating and also electricity. And so we can create different fuels in the step number 5. What is also excluded from the waste stream is the inert material and the scrap metal. And here, when you have seen pictures how dry this waste is after the drying step, and in this stage, it's very easy to separate scrap metal and small glass pieces, mineral pieces from this waste stream. Of course, as a prerequisite, you need a loose and homogeneous and free-flowing material. You need a specified consistent moisture content. You need absolute dust-proof encapsulation because when the waste is so dry, you have a lot of dust all around. And you need a trouble-free, just-in-time logistics. So as soon as a container is full with RDF, it has to be dispatched. But this is not so difficult to handle if you have the right concept. And of course, we can assist you with the right. So let's have a look what comes out of this MYT process. So what I just want to tell you here is from waste acceptance, so from the first step until the output of the products, we need only 14 days. So the waste stays in the treatment facility 14 days, no more. When you compare this to other mechanical biological treatment systems, you know that it is very fast to process waste in 14 days, such a system. So, of course, we have minerals, we have RDF with a high calorific value, and we have RDF with a middle calorific value, which is mainly the biomass RDF. You see the small minerals here on the left-hand side. So it consists of small stones, glass pieces, porcelain pieces. But what you see here is the quality, how it comes out of the system. These minerals and glasses have not been washed. They are as clean. The same applies to the RDF. This is how the products come out of the system. So the high calorific RDF contains a lot of plastic, also paper. And the mid-calorific RDF has a high biomass share. So I give you more insights into the RDF. So we have, like I told you, we create actually 6 different fractions of RDF. So we have the very small RDF, it's 0 to 8 millimeters. It has a big biomass share. So if you incinerate this, you get CO2 certificates because most of this RDF is climate friendly and CO2 neutral. Then we have the middle size RDF, which has a bit higher calorific value because there's already plastics in. And then you have the bigger RDF, 30 to 80 millimeters, which consists mainly of plastics, which has a high calorific value. And again, the minerals. We just put the euro coin beside just to give you impression on the size. And we name it normally in Germany RDF, refuse-derived fuel. But when you work with the cement industry, you will come across the name SRF, solid recovered fuel. SRF normally refers to a process, and the RDF has to undergo a process to name it SRF, because it has you have to maintain a high quality, you have to be low in pollutants, the chlorine content has to be low, otherwise the cement industry cannot make use of your RDF, especially when it comes to chlorine. So let's have a small comparison of the quality parameters of the MYT substitute fuel with coal, but not hard coal, but lignite coal. So you see a small difference in the calorific value, and water content is nearly the same. In sulfur, the MYT RDF is quite low, but here you cannot take these numbers and apply it to everything, because it is important where the waste comes from, where it originates from. If you collect, for example, waste from industrial areas, or you have a very high salt content, for example, in your water, this all goes into the quality of the RDF. So of course we have to see what waste are you collecting, where it comes from, and then we can also estimate the quality of the RDF during the design phase of the facility. What is extremely interesting here is the carbon content, especially when it comes to biogenic carbon. If you see, of course, dry lignite is a fossil fuel, you have no biogenic carbon, but with the MYT RDF, due to the organic waste fraction, you have a high biogenic carbon share. And this is actually what we have to go for the future to protect our climate. Oxygen is quite similar, and one big difference, which I have to name here also, is the ash content. The MYT RDF contains a higher ash portion. When you've seen the slurry, maybe this also, if this also makes it clear why you have more ashes inside, because we are producing a slurry first, which we dry down. But this ash content is not a big problem. If you work together with the cement industry, they love the ash content, because the ashes stay in the product, in the cement, and this allows the cement industry to reduce their resources to put into the cement, because they can use the ash. And of course, if you use it in industrial power plants, you need to be aware that you have a higher ash content, and that you have to landfill these ashes or use these ashes as filling material, for example. The output of the MYT process. You have seen this picture at the beginning when we've seen the waste characteristics which was going into the MYT facility. I just want to recap with you. From 100,000 tons of waste, we exclude about 40,000 tons of water, which we can make use of for agricultural irrigation, for example. We have tweaked our MYT system a little bit, and also from 30% organic waste share, we are now able to produce 7% of biogas, or 7,000 tons. In the beginning, we had only about 5%, but now it's a bit more optimized, the system. And if you have a very high organic waste share, you can estimate here more biogas output. Of course, we produce from 100,000 tons of waste, we produce about 40,000 tons of fuels, refuse-derived fuels, and we regain the metals, the minerals, and we have always a small rest, which is better to landfill, about 2%, and the losses I explained to you before, it's organic material which was used as foodstuff for our microorganisms. So, what to do with the RDF, and let's have a look at the energy balance and towards the CO2 savings. About the RDF usage, I told you already, it's a wonderful material for the cement plant. So actually for our reference facility in France, for the second MYT facility which was built, the cement industry was partner in the project because they knew about the good results of the RDF in Germany, and they wanted to make use of all the RDF material then in France for the cement industry. Another application is a paper plant, which has its own industrial power plant, and they also make use of our Kahlenberg RDF. This is power and heat generation plant about 120 kilometers, I think, from the MYT facility, roughly. And they use hard coal from Colombia and South Africa normally, which has to be imported to Germany. And now they can substitute 25% of their hard coal by using the MYT RDF. This is, to me, one of the most important slides, and I would like to explain it to you. So this green column shows you the energy potential, which is delivered to your waste acceptance hall over the year. So it's 235,000 megawatt hours per year. This is the energy potential, which is delivered to your facility when we estimate about 7 megajoule per kilogram as calorific value of the waste, and we are having about 120,000 tons of waste. So this is the energy potential. But just as the waste comes, you cannot make use of this energy. By applying the MYT process, we can regain nearly 90% of the energy potential which is brought to the facility. We can regain in energy carriers, in RDF and biogas. So it's about 165,000 megawatt hours per year of energy within the RDF, and another 40,000 megawatt hours per year of energy within the biogas. Like I told you, we have losses, and it's organic material, so we lose about 30,000 megawatt hours per year. And now the astonishing part. The MYT facility requires only 25,000 megawatt hours per year of energy. So if you put the red and the yellow column on top, you have regained nearly 90% of the energy in energy carriers. And when you deduct the own consumption of the MYT facility, you still have about 75% of the energy which is brought to your facility. You have it ready in your energy carriers, in RDF and biogas. And this is why MYT is not only a waste treatment facility, it's also an energy production facility. It produces energy. It leaves you with much more energy than you invested for treating the waste. This is a very good news. And when you have waste management and energy production in one hand, you can make it economic, and you can make it you can set it up in such a way that your municipality really benefits from this. And not only the municipality, also the environment benefits very much from an MYT process, because the annual CO2 savings from only 120,000 tons of household waste gives you about 82,000 tons of CO2 savings. And this climate-friendly electricity and heating energy is obtained from the energy carriers biogas and high biomass energy content RDF. High biomass content RDF. So these CO2 certificates only, of course, only come from the biogenic share of the waste, and it's from the biogas and from the RDF biomass. Biomass RDF, exactly. Okay, and now we go towards the other references of the MYT technology. So as you can see, the Welle is establishing several MYT projects in China. Then, of course, we have Onut in Bangkok already under operation. I will show you the details now in the next slides. And of course, we have a facility in Zumwalt in France. This is the one where the cement industry is partner, because they want to have all the RDF from this facility. And of course, the first one was the reference plant in Ringsheim, the ZAK facility, where I showed you all the pictures. Now let's have a look towards Onut. It's within the Bangkok Municipality Administration at one transfer center in Bangkok. Bangkok has 3 transfer stations. It's quite small, only 3.6 hectares. It's processing 800 tons per day. And here the moisture content of the MSW is 54%. And when you look towards the characteristics, looks quite different to what we receive here at Ringsheim. It has nearly 50% organics, then 25% of plastics, 13% of paper, wood, a small portion of glass, textiles, metals, bones, and shells. Okay, let's see how we adapted the MYT process to treat the waste in Bangkok in the most economic way and make use of it. So first, 800 days per ton are delivered to the facility. Right away in the and here we have a debunker because the informal sector has taken out all the valuable stuff already. Only a little bit of recyclables and metals are in, but the valuable stuff is out. So it can go in a debunker and it goes directly in the pre-treatment system. Here the fuels, so the RDF1, which are mainly the plastics, are excluded. The metals are taken out by magnets, and we have inert materials, so the bigger parts, which can be taken out here. Of course, everything is going under an odor treatment unit to produce clean air and to reduce the odor nuisance, because actually the smell at this transfer station, which comes from the composting plants and the other facilities which are there around, mostly composting and sorting facilities, the smell is horrible. So MYT is doing a very good job in reducing the odor at site. Then it goes directly into the biological step, which is here the step number 2. In Ringsheim it is step number 3. And here the other fuels are created and the inert material excluded from the system. And then this waste material goes into the anaerobic digestion systems. And then, of course, everything like explained, we have the wastewater treatment, and of course, from the anaerobic digestion, we create a lot of biogas. The biogas is used in a cogeneration system for heating energy and electricity production. And here you have the table. So from 800 tons per day, MYT produces nearly 500 tons per day for sale of RDF 1 and 2. And in Bangkok, the industrial power plants are actually designed for a lower calorific value, so they can make use directly of the RDF 1 and 2. And they have also a very nice purchase price for the RDF. So the RDF is sold to the industrial power plants. And the total electricity which can be produced via biogas is about 3,201 kilowatt hours per day. So the plant uses only 1/3 of the biogas energy. And for grid connection, for sale, we have more than 2,000 kilowatt hours per day. We got a green tariff in Bangkok for this biogas. And this is how this whole process or the investment is refinanced through the sale of RDF and the sale of electricity. This is covering the complete investment costs and operating costs and the financial costs. So it's a wonderful. Here you can see the pictures. So on the left-hand side, you see the RDF1, which consists mainly of plastics, and the RDF2 is the material after the pressing, after the mixing and pressing. It's of course low in the calorific value, but it's still good enough for sale in Bangkok. So it all depends on the framework conditions in your location. Here you see the design of the facility. As you have seen on the picture of ZAK, ZAK was built on a slope. We had 5 different buildings. Every building was assigned to a certain step. Here we were building the MYT facility on flat land, and it was actually very difficult flat land because it's in a muddy area, or not muddy, it's in a lowland area of Bangkok. And in the underground, they had to pile in the underground to set the foundations for the buildings. But this is all possible and all to handle. And here you see that the facility was built more or less in a line, but also a bit in an U shape. So you have the waiting system in the beginning and the office building, and then you have here you have the discharge workshop where the waste is discharged. This is the first step, the mechanical pre-treatment. This is in blue. The order treatment is taking care of the air in the whole facility. Then you go over to step number 2, which is biological conversion. So you have the biological hydrolysis system, which is the mixing. You have the dewatering workshop, which is the presses. You have the leachate pre-treatment workshop, where you take care of the process water. Then you have the wastewater treatment workshop, which is the cleaning of the waste water. You have the machine repair workshop, the anaerobic digestion. Of course, you need the RDF storage until you dispatch it to the industrial systems. And the desulfuration facility is the biogas cleaning. You have the biogas tank, and then you have the generation unit workshop, which are the CHP systems. What I would like to add here is the following. I told you before that in the mixing process, you apply process water to the waste, about 1 ton of waste, 1 ton to 1.5 tons of water. Now, of course, you will ask in Egypt where to take this water from, because we are living in a dry area. You do not need additional water for the MYT process. We work with the water which is inside the waste. So every moment we get more water into our system with the fresh waste. In Egypt, you have 60% organic waste, more or less 50 to 60%. So you have sufficient water inside your waste to make this MYT process work. Even with 30% of biogenic waste in Germany, we do not need additional water for our process. So the water inside the waste is extremely sufficient, and we take this process water also in a cycle. This I need to tell you. So we have the fresh water, which is coming with the new waste. We have the process water. We have this process water used in a cycle. So after cleaning, it is again applied to the fresh waste, used again, cleaned again. So it's a cycle, and we get always more water inside with the fresh waste. So you do not have to worry that you need too much fresh water for running an MYT facility. Here you have the bird's eye view on the MYT facility in Bangkok when it was erected at Onut. This is the entry. And here we also we have a deep bunker, we can work with a crane. So there are many ways to set up this MYT process in a more economic way, as you have seen it in Ringsheim in Kahlenberg. Of course, that was the reference plant, the first plant. There we wanted to show how far you can go with waste treatment. Of course, if you want to have the optimum in cost effectiveness and operational costs, we can discuss with you how to design this MYT facility to reduce also the cost of investment, but still have the same standards in environment and human protection. This is important to us. Here you see how the sieve drums have been put on in Onut, the mechanical pre-treatment. Here, this is the MZRs, the mixers and the dewatering presses. And on the other side, the leachate pre-treatment system. So this is the water treatment. So here you have the anaerobic digesters and the biogas utilization. And this is actually the end of this presentation. And I thank you very much for your attention and for your time. And I hope now much more is clear to you. Please come back to me if you have any further questions. I will be happy to answer them. Thank you so much.